Welcome. In today's video, we are going to derive maximum likely estimators for the parameters of a log normal distribution. So to begin with, let us set up our problem. So suppose we have a series of random variables, x1, x2, all to xn, and say that they are independently and identically distributed with a log normal distribution with parameters mu and sigma squared. Then we can write that then the PDF, or the probability density function of xi, is given by the following. So I'll put in f subscript x, xi, given our parameters mu and sigma squared, is equal to 1 on xi sigma square root 2 pi exp of negative log xi minus mu all squared all over 2 sigma squared. Now, alternatively, we can actually write it in this form, and this form will be easier just to do our computations. I'm going to say let tau equal sigma squared. Then we can actually rewrite our our probability, let's say our probability density function in the following way. So we can say mu and tau are our parameters. We can now replace this part here as the square root of 2 pi tau, all inside the brackets, and we can replace this sigma squared as a tau as well. So that's just going to help us do a little bit more of, make our calculations easier. It ends up, when you solve for the maximum likelihood of tau, you just take the square root of it to give you the maximum likelihood estimate of sigma. So all good there on that front. So now let's begin. The log likelihood, just the likelihood function evaluated at mu and tau, given our set of data x, is by definition the product of I equals 1 of all the probability density functions evaluated at xi. That becomes the product of I equals 1 to n. In this case, I'm going to copy this across, and we've got our expression here, and I'm just going to take the product of those terms. Now, this can be broken up or broken into several components. The first component is the 1 on xi's, so I've got the 1 on xi's all multiplied by each other. Then I've got the product of I equals 1 to n of, now you've got the 1 on square root 2 pi taus. Now, for simplicity, what I'm going to write this as this can be rewritten as 2 pi tau to the negative 1/2. The half giving you the square root, but the negative making it 1 over the square root. And then finally, we have the product of I equals 1 to n of our exponential term, and that can just stay as is, exp of negative log xi minus mu all squared over 2 tau, close brackets. Easily accomplished. Now we can do a bit more simplification. So here, what we'll have is the product of 1 over xi's, which will be 1 over x1 times 1 over x2. The numerators, when multiplied by each other, will just be 1 times 1 times 1 times 1. So you're left with 1 on top of the numerator. And then the denominator will simply be all the product of the respective xi's. So I can write it like that. And in fact, for simplicity, what I might write it, just so it looks a bit easier, I'm going to write it as, instead of 1 over xi, I'm actually going to write it as the product of xi's to the power of -1, just so I don't have all these powers, or just so I don't have to keep writing fractions. Similarly here, or not similarly, but you can see here that the index I actually doesn't appear in the second lot of terms, which means when we multiply I equals 1 to n, this is actually just equivalent to multiplying the term in the middle by itself n times. So when you multiply this by itself n times, you just get it to the power. So you get 2 pi tau to the -1/2, and then all of that to the power of n. And then finally, when you take the the product of exponentials, remember these are powers, remember a product of powers is the equivalent to the power of the sum of the exponents. So in this particular case, this becomes exp of the sum of I equals 1 to n of negative log xi minus mu all squared all over 2 tau in brackets. Pretty nice. Now again, I'm just going to rewrite this a little bit here. First term, I'm just going to copy that. No issues there. That won't change, at least for the time being. So we'll leave it there. This component here, where we've got the 2 pi tau to the -1/2, notice when you can use one of the power laws, we've got -1/2 and then further to a power of n. That becomes the equivalent of taking the base to the power of -1/2 times n. So in this particular instance, we get 2 pi tau all to the power of -n on 2, which is a nice little simplification there. And then I suppose with this component here, what we can do, there are a few things, but mostly for the time being, I notice that I've got a -1 on 2 tau that I can take out as a common factor in this summation. And that's actually what I'm going to do. So it'll give me exp of -1 on 2 tau, the sum I equals 1 to n of log xi minus mu all squared. And there we have our expression. Now, the log likelihood function, ln of mu tau given our data x, is by definition log of the likelihood function, which I'll just write out here, which in this particular instance is log of this entire expression above. So I'm just going to copy that expression above for a second, copy, paste, and hopefully I'll be able to fit the log in. If not, I might just have to bring the equal sign a little bit out the front. So it's log of that entire expression. And we know from our individual experiences with log that when you take log of a product, and notice this is 3 terms multiplied by each other, that is the equivalent of taking the sum of the logs. So the first term, we can take log of the product of I equals 1 to n of xi to the power of -1, plus log of the second product, 2 pi tau to the -n on 2, and we'll keep that one, plus, and then I guess in our final component, I might write it down here, log of the last expression, which is exp -1 on 2 tau, whoops, not 2 pi, but 2 tau, 2 tau, I equals 1 to n, log xi minus mu, all squared, close off the exponential and close off that log. So this is our expression here, and what I'm going to do now is I'm going to take a copy of this expression so that I can bring it to the next page, because I've run out of room on this page. So let me do that now. Here is our expression. Here is my, oh, well, let me bring it up so I've got more room. Here it is. Nice and easy. So this expression here now becomes, well, for the first log term, we can take this power, this -1 power, and we can bring it down the front here. So we get negative log of the sum of I equals 1 to n of xi's. Simple and straightforward. The next component here is, again, we've got a power inside a log function, so we can bring that power at the front. -1/2 or -n on 2, so I'm going to bring that down, -n on 2, and we've still got log whatever was inside, 2 pi tau. And then finally, I've got the final expression here. Notice in this particular instance, we're taking log of an exponential function, so that just leaves us with the power inside the exponential function. So in fact, we can now write 1 on 2 tau sum of I equals 1 to n, and I always like writing the log xi minus mu, all squared at the front there, or at the back, I should say. Now, we can probably do one little bit of simplification, and that one little bit of simplification, oh, actually, no, there's a few, two more bits of simplification. I should apologize there. The first bit of simplification is to note that when you have a log of a product, that is the equivalent of the sum, well, I should probably write it here, is the equivalent of taking the sum of the logs of the individual components. So log of a product is the same as sum of logs. Equivalently, here we can sort of utilize the same concept where we've got log of 2 pi tau. We can think of this as 2 pi times tau, and so we can separate this component as log of 2 pi plus log of tau. So doing that, we get -n on 2 log of 2 pi, and then we've also got log of tau. Now, just remember though, we still have this -n on 2 of the front operating on both, so I'm going to write -n on 2 here. And then of course we've got our final expression here, which I'm just going to copy and paste instead of rewriting, just for simplicity. And I'm going to make it just look a little bit nicer for you there. And there we have it. We have our log likelihood function. Now, Now that we have this log likelihood function, what we need to do is we need to compute a few derivatives. So these derivatives can be expressed in a few ways, but what we're going to do is we're going to take the derivative with respect to tau and with respect to mu. So let's start off with the easier derivative to take. Mu tau given x bar with respect to mu. Let's have a look. First term doesn't depend on mu, easy. Second term doesn't depend on mu, so when differentiated goes to 0. This term doesn't depend on mu, differentiated goes to 0. The only term that does depend on mu is this term here. So I will probably rewrite this as the derivative with respect to just the last term. We can just focus on the last term. 1 on 2 tau, sum I equals 1 to n of log xi minus mu all squared. Doing that gives the following property, or the following result. We've still got our negative 1 on 2 tau at the front. I'm not going to change that. Now, what we do have though is, and before actually I go into a little bit more depth here, I want us to recognize that when you take a derivative, even a partial derivative, and you've got a product, and then you've got a sum, right? We can actually take the derivative, and let me be clear, a product which is independent of of the variable we are differentiating by. What we can do here is this is the equivalent of bringing through sum I equals 1 to n of d on d mu of log xi minus mu squared. So just to reiterate what I was trying to get my point across there is that when you've got a partial differentiation or a normal differentiation with respect to a particular parameter, and all these terms, and what we have is a series of what we could say is functions of mu, which are summed together, and then we're also multiplying by a scaling factor, we can actually take the partial differential, or we can take the partial differentiation with respect to mu through the summation, and actually through the scaling factor as well, to give you your term. And as an aside, this is kind of the equivalent of saying, if you've got d on dx of alpha f of x plus beta g of x, as we have here, where I guess in this particular case, your negative 2 tau or negative 1 on 2 tau is kind of like your operators at the front, and your summation here is the sum of two terms. We can equally write that as alpha times f dash of x plus beta g prime of x. And that's really what I'm using here by virtue of the fact, by virtue of this fact here. I thought I'd just point that out in case that step wasn't as clear. So now that we've got that step here, we've still got our negative 1 on 2 tau. We've still got our summation here of I equals 1 to n. And now we can take derivatives with respect to this function here. So the first point to note is that we need to, when we've got a function inside of a function, which happens to be a polynomial. So to differentiate a polynomial, first we need to note that we take the power down the front, and then take 1 off the power, or log xi minus mu. We take 2 minus 1 off the power. And then we need to multiply by the derivative of the inner function. Don't forget that. And the derivative of the inner function, at least with respect to u, is just -1. So that gives us times -1. So our next step involves a little bit of simplification to note that the 2 here in the fraction or the denominator of the opening fraction and the 2 here can actually cancel with one another, the 2 and the 2, and the -1 and the negative out the front can also cancel with one another, basically leaving us with 1 over tau, the sum of I equals 1 to n of log xi minus mu, all in brackets. We can now also compute the second derivative. So the second derivative of the log likelihood function with respect to the data. And we can do that with respect to mu twice. And of course, the second derivative is just the first derivative of the first derivative. So we can write d on d mu of 1 over tau I equals 1 to n of log xi minus mu, again in brackets here. And similar to the first case where we found that the derivative of a scalar times a sum of functions can actually be rewritten as the scalar factor times the sum of the derivative of those respective functions. So I'm just going to write that out now, -1, which is quite nice. And then, of course, we still have our 1 on tau at the front. Still going to have our sum I equals 1 to n. The only distinction now is we can evaluate this derivative. And when we take the derivative here, we notice this is the only term dependent on mu. This mu, when differentiated, just gives us -1. So we just have a series of -1s. Noting that we have to add -1 n times to itself. And so altogether we'll get -n on tau, which is a nice, again, simplified form. Brilliant. Let's move on to finding the derivative with respect to tau now. And I'm going to do that. I'm going to take a copy of our likelihood function again. Paste that out. And here we have it. Our likelihood function, ln mu tau, given our data. Now, with respect to tau, we can take the derivative Tn mu tau given our x bar d tau. In this particular instance, we've got a term that doesn't depend on tau, so we forget about it. A term that doesn't depend on tau, so we can ignore it as well. And then 2 terms which do depend on tau. So let's put those through. So this will be the equivalent of taking the partial derivative with respect to those 2 terms that I highlighted above, which do depend on tau. And for the second term here, the 1 on 2 tau, I'm actually going to rewrite that as a half tau to the -1 sum I equals 1 to n of our log xi minus mu all squared. And that's just because that form there, or a power form, is easier to differentiate. So, for the first term, we note that when we differentiate with respect to tau, we've just got a log of tau. Differential of a log, or differentiating a log, gives you 1 on the variable that we're interested in. So then this becomes 1 on n to tau. This one here, because it's in power form, we can get a little bit more of or we can get a bit clearer explanation. We've still got the half scaling factor. We've now got to take the power down the front, so we've got a -1. We've got to now take 1 off the power, which gives us -2. And then finally, we still have our summation, which with respect to tau is actually a constant. So we don't need to worry about that. It can just multiply there at the end. And then after maybe one line of simplification, we can rewrite this as negative n on 2 tau, 1 or plus 1 on 2 tau squared, 2 tau squared, I equals 1 to n of log xi minus mu square root. And you can start to see why I've sort of put in my taus all the way when we first started this video. And the reason for that was if we were to differentiate with respect to sigma squares and things like that, it becomes a little bit complicated. But looking at it through the perspective of tau, we sort of get there. So now that we've accomplished that, let's take the second derivative. And so the second derivative, ln of mu tau given our data, second derivative with respect to tau is equal to the derivative d on t tau of the term we just came up with. Copy that across. The only distinction is now I'm actually going to go back to the original formulation I sort of had, and I'm going to write that 1/2 on tau squared as tau to the -2 again, just so I can take this derivative. So in this particular, and also actually the front term I'm going to replace as n onto tau to the -1. So that 1 on tau here becomes tau to the -1, again, for simplicity. So after that, we can take the derivative. We've still got our -n on 2. Here, the -1 drops down the front, so that gives us times -1. We take 1 off the power, that gives us to the power of -2. Similarly here, what do we have to do? We have to take the power down the front, so this becomes plus 1/2 times -2 tau to the -3. And then of course we still have our sum of, or maybe I'll just write it, I equals 1 to n of log xi's minus mu's all squared. And then as a nice reward and some nice simplification here, we're going to multiply these out. So this gives us, that first term gives us n on 2 tau squared, which is a nice property or a nice simplification. And then here we note that the 2 and the 2 here will cancel out. So we're just left with minus 1 on tau cubed sum I equals 1 to n of all the log xi's minus mu's all squared. And there we have it. We've done our differentiation with respect to tau. Finally, we also need to compute one other derivative when we're going to solve for, or when we need to prove actually maximum likelihood estimate, or maximum likelihood has been achieved. And that is the second derivative of the log likelihood function. But in this case, we're going to differentiate with respect to mu and with respect to tau. Now, it's up to us which one we're going to use. I'm more inclined to use, this is the derivative with respect to tau of the derivative with respect to mu that we've already calculated. I'm more inclined to use this approach. So if I now find out what we differentiated before, or the first derivative with respect to mu, I might need to go to the old page. Here it is. Here is our expression. We'll copy that across, paste that through. Yeah, that's a much nicer expression. And then, of course, just for simplicity, I'm going to turn that 1 and tau at the front to a tau to the -1. And then we know that we need to take the power down the front, 1 off the power, and we've still got our sum here, I equals 1 to n of the log xi minus mu, all here. And then quite simply that becomes -1 on tau squared, and for the sake of efficiency, I'm just going to copy that and put it there. And so now we have derived our first derivatives, our second derivatives, or our partial derivatives, I should say. We can now finally solve for the maximum likelihood estimates of the log normal distribution. So let's go about our day. Firstly, to solve for the maximum likelihood estimator of mu hat, we need to solve dn of mu sigma squared with respect to mu, evaluated at mu, and apologies, I remember now that I've changed the formulation, so it should be with respect to tau. So mu tau is equal to mu hat tau. Recall that the condition is that that has to be equal to 0. So if we go back and find our first derivative with respect to mu, copy this across and paste in our expression, except we are now evaluating not just at tau, but we are evaluating at tau hat and mu hat. That has to be equal to 0. Then our next step in this equation is to recognize that the tau at the front doesn't actually matter. We can multiply both sides by tau and still be left with the I equals 1 to n of log xi minus mu hat all together equals 0. Then we note that we can actually take, because it's a sum, or it's a sum of subtraction, we can actually rewrite this as the sum of I equals 1 to n of log xi's minus all the sum of I equals 1 to n of mu hats is equal to 0. And then again, got more simplification. We've still got the I equals 1 to n of the log xi. Now, in this case, because we're summing mu hat by itself a multiple of n times, we can actually rewrite that whole summation as just n times mu hat. And because that's n times mu hat, I'm going to move it to the other side of the equation as well. So that gives us n mu hat. And finally, after some solving here, quite a rigorous process, it becomes 1 on n times I equals 1 to n of log xi, and I'm going to give this the formation log xn bar. I'm going to define it as a log xn bar. And we've finally solved for our value of mu. We can now solve for our value of, well, tau. So, again, our formulation will be something of the sort. We've got the first derivative with respect to mu tau given x bar over tau, with the condition that mu tau is again equal to mu hat tau hat. Called the condition is must be satisfied for maximum likelihood estimation that the derivative is equal to 0, because that's when we find either local maximums or local minimums. Now I've got to find our expression here. We had it here before. Here it is. Copy this. Bring it to the next page. So here is our expression. This has to be equal to 0. Noting again, we need to substitute in the maximum likelihood estimates. Now, first point of action is to note that we can multiply, if we multiply both sides by tau hat squared, in fact, 2 hat tau squared for that matter, we can remove the fraction completely here, and we can also remove the fraction here, and we'll be left with a factor of tau. So if we do that, we've got negative n tau plus the sum I equals 1 to n of log xi minus mu hat all squared is equal to 0. Again, just as a side note, I multiplied both sides by 2 tau squared, just in brackets here, to give me my next formulation. Then, of course, we can move this particular piece, or effectively solve for tau now, and what we'd have to do is we'd move this n tau to the other side, and then we could finally divide both sides by n. So this actually leaves us with tau hat is 1 on n sum I equals 1 to n of log xi minus, now our mu hat, I'm going to substitute in the expression we derived for mu hat above, which was the average value of the log x's of our data set here. And here we have it, we have our maximum likelihood estimates. Now, to actually prove that the maximum likelihood estimate is achieved, especially when we're using two variables, unfortunately what we're going to need to show two particular facts. Fact number one, and I'm not gonna, or I could write them down, but I might as well. Fact number one is we need to show that the derivative with respect to mu tau d tau evaluated at mu tau equals the maximum likelihood estimate. We need to show this to be true. We also need to show a second condition, but let's first begin with this condition, and then we'll get to the second condition for differentiation. Or in fact, maybe let's write it out as well. We need to also show that the derivative with respect to mu tau given x bar all over d tau squared multiplied by the same thing, copy that, multiplied by, instead now, the second derivative at tau. Sorry, I meant to put the second derivative in the first condition. This condition, and then minus the second derivative, ln of mu tau, given x bar all over d mu d tau all squared, evaluated at, again, the same conditions, at mu hat, tau hat. We need to prove that this is greater than 0. Again, I'm just going to put at mu tau is equal to mu hat tau hat. Just for clarity, it needs to be true at those points. So, let's begin with proving condition 1. So, we're going to take the second derivative, or the second derivative with respect to mu. I believe I evaluated it on this page here. So here is my formulation that I came up with. Copy this. Let's go to the next page. Paste that in. We've got our formulation here. So this derivative actually has to be less than 0 for all values of tau, which can only take values from 0 to infinity. So we've proved the first point. Condition 1 is satisfied by virtue of the fact that we've got a negative out the front. Nice and easy. Second point to prove, unfortunately, might be a little bit challenging. So here we had all our terms that we needed to evaluate. Second derivative, and then the second derivative with respect to mu and tau. So, and then we had to evaluate them at the respective maximum likelihood estimates. So let's begin. The second derivative, well, quite simply, the second derivative, the first component, copy that, paste that, evaluated at mu tau is equal to mu hat tau hat, is by definition equal to, well, we wrote it actually up before here. It's given by n, negative n on tau hat. Solved for that one. The second term that we had to prove here in this component was the second derivative with respect to tau squared. So let's find out where we solved for that. That was here. So I'm going to take this particular expression. In fact, I'm not just going to take this expression. I'm going to take the whole expression here, copy that across, and we're going to put that here. So this expression evaluated at, in particular, tau is equal to tau hat, is by definition equal to the following expression, and I'll place that on top of each other. Evaluated, remember, we're evaluating at the maximum likelihood estimate. Now, here's an interesting point to note. If I go to the previous page, where I came up with an expression for tau, or tau hat more importantly, you'll notice here that if I slightly rearrange this equation, I can see that the sum of the log xi's minus log bar or log xn bar all squared is actually equal to n multiplied by tau if I cross multiply the n. So where I see the sum of log xi's minus mu hat, which again was the average log, I can now actually rewrite this expression, so these stay the same, but I can rewrite this expression as times n tau hat as our next expression. Doing a bit more simplification, that becomes n on 2 tau squared minus this tau cancels with one of the taus in the denominator to be left with 2. So it becomes minus n on tau hat squared. And then after a little bit more simplification, we can recognize this as n on 2 tau hat squared minus 2n on 2 tau hat squared, basically using or finding a common factor between the denominator, which is just 2 tau squared, and then we can recognize that this is negative n on 2 tau squared. And so we've got a nice expression there. And finally, we need to, again, in this, remember to prove maximum likelihood estimate or maximum likelihood has been achieved, we needed to find this last component evaluated at the respective points, at the respective maximum likelihood estimates. So let's find that point that we found before. So here it is. Let's take a copy of that, or let's actually take a copy of the whole value here, copy that out, paste it in. Whoops. Might be a little bit challenging to, whoops. I'm gonna need to retake that copy across because it didn't perfectly come through there. Copy that now, paste it in here, and now we need to remember to evaluate this at mu tau is equal to mu hat tau hat, which now we're going to put into our expression, which in this particular instance, we're going to put our hats on everything, is equal to, well, quite simply, we're going to recognize that the condition of mu hat, if you recall the condition of mu hat, going back to when we originally solved it, was that, or one of the solution, or when we actually solved for mu hat, we solved it in such a way that the sum, or one of the steps in those equations was to actually solve for this expression is equal to 0. And therefore, by that account, if we go back, we've got that same sum here, and so that sum will actually just collapse to 0 if we were going to simplify it. So the whole expression collapses to 0. And so if we now take this entire fraction here, or this entire component that we've been trying to evaluate, or the second condition that we've been trying to particularly point out, and I'm going to turn it into white. We've got to evaluate it again at mu tau is equal to mu hat tau hat. We've come up with all those expressions now. the first expression with respect to mu squared, where did we calculate it? Here it is. Copy. The second expression that we evaluated with respect to tau squared, or tau, sorry, the second derivative with respect to tau, we evaluated it here. Here it is. Copy. Paste that down. And then finally, minus. Well, we evaluated also the second derivative with respect to mu and tau. We know that that is equal to 0. And so after this expansion, we are left with minus, or not even minus anymore. We are left with positive because the negatives cancel out. Got n squared on tau hat cubed, which by definition is less than, or sorry, is greater than or equal to 0. And we finally proved that it is in fact a local maximum, because we've proven the first step a while ago, the first condition, but the second condition now we've just proved is greater than 0. And it follows that our maximum likelihood estimators, which we've had before, again, for mu, if you recall, mu hat was by definition the average log of all our data, and our tau hat, or in fact we can now go back to our sigma squared hat, is by definition the maximum likelihood estimate we came up with before, which is this expression here. And I'll copy that across, paste it here, and I will overlay it, put in the style of green so it matches. And there you have it, ladies and gentlemen.